let's go ahead and talk about the chain rule. If there are other things people want to see, classifying extrema, other stuff, the gradient, we can go there as well. So let me close this. All right, let's start off with an example. So the pressure, thank you, P measured in kilopascals, and the volume, V, measured in liters. My mom is calling me. Of course, she's calling me right now. And the temperature, T, is measured in degrees Kelvin of 1 mole of an ideal gas are related by the ideal gas law, which you have probably seen before if you've ever taken chemistry. PV equals, well, PV equals nRT, but nR at this, for this particular problem is approximately 8.31 T. So now, if the temperature of a gas is 300 degrees Kelvin and is increasing at a rate of 0.1 kelvins per second, and the volume is 100 liters and increasing at a rate of 0.2 liters per second, how fast is the pressure changing? Welcome. Don't worry, we're just trying to use some real world examples. It's going to be mostly mathematical. So it's not too scary. I'm not a huge chem fan either, but it seems like it's a good kind of real equation examples. Like if you like, this is something you could actually be asked. Like if you have this thing, you know what its volume is. My nose is really itchy. You know what its volume is. You know what its temperature is. You know how those things are changing, and you want to know how is the pressure changing. So first of all, I need to write pressure as a function of volume and temperature. So I'm going to solve for P here and say that P is equal to 8.31 T divided by V. Or probably more conveniently, P is equal to 8.31 times T times V to the negative first. And then, oh man, my nose is super duper itchy. And both temperature and volume are functions of time. Now, I know we haven't written that explicitly, but it is made implicit by the fact that we were talking about how they're changing. Right? We're saying that the temperature is changing at a rate of 1 kilopascal per second, sorry, 1 Kelvin per second, sorry, 0.1 Kelvin per second, oh my gosh. And that the volume is increasing at 0.2 liters per second. So those things are saying, oh yeah, those are functions of time. They depend on time. So we're going to draw this diagram of how things depend on each other. First, at the top level, we have pressure, and it's immediately a function of both volume and temperature. But then volume and temperature are both functions of time. And if we want to find the derivative of pressure with respect to time, we want to know how pressure is changing as time is changing, we're going to find all the paths from P to T. So to find the derivative of pressure with respect to time, we need to find all the paths from P to T. So First, there's a path that goes through volume. So PV and then VT, or as I say, from P to V, we're going to take the partial derivative. Actually, first I say we're going to find dP dt. We're going to have this path from P to V, which is going to give you del P del V, and then times dV dt. Take it from here to here and then from here to there. Plus the other path from P to T through temperature. We're going to have del P del T times dt dt. I wouldn't stress too much about the del's versus d's, but I will point out I'm saying del P del V and del P del T because P is a function of multiple variables. It's a function of volume and temperature. I'm saying dV dt and dt dt because V and T are both functions of only time. They don't depend on something else. So that's why there's a difference there. But again, if you wrote del or d, no one's really going to look that close to see if it's curly or not. So let's find the things. Let's write it again so we have it on this page. So dP dt. I'm saying d and I'm still kind of writing it like a del. And then del P del T times dt dt. So we need all the things. We have P equal to 8.31 times T times V to the negative first. Del P del V is going to be 8.31 times T times negative V to the negative second. And del P del T is going to be 8.31 times V to the negative first. Those aren't so bad. And then if we're plugging in at T equal to 300 kelvins and V equal to 100 liters. All right, so let's throw it all into the formula. So my derivative with respect to time, or how pressure is changing with respect to time, is going to be del P del V, which is this with these numbers plugged in. 8.31 times 300 kelvins times negative 100 to the negative second. And then we're going to multiply by dV dt, which was given in the problem. The rate of change of the volume was 0.2 liters per second. So just to emphasize what's what here, there's my del P del V, there's my dV dt. Plus, then we're going to go the other way. Del P del T, that's just this. We're going to plug in V equal to 100 again. That's going to be 8.31. I didn't really mean to include the units there, but I did because I'm a fool. Sorry. I don't like to write the units until the end, right? Writing them in the middle of the problem is just like a recipe for disaster. Then we're going to have times 100, negative first. And then we're going to multiply by dt dt. And the way the temperature was changing was at 0.1 kelvins per second. And then you use your calculator because no one's calculating this by hand. And after you do all the calculations, you're going to get approximately negative 0.04155 kilopascals per second. But the point of this is more, right? I mean, the numbers, okay, who cares about the numbers really? They're not that important. The point of this really is that if you're differentiating a function of multiple variables that also depend on something else, we make this diagram, or I forget, this branch chart. I don't know, there's various names for it. I always just think about it as the functional diagram, where you think about what your top level function depends on and then what each of those things depend on. And then we find all the paths from here to here. So typically, right, to get from P to V, you're finding del P del V. To get from v to t, you're finding dv dt. To get from p to t, you're finding del p del t. To get from t to t, you're finding dt dt. That's the main gist of what's going on here. So whenever you have to use the chain rule, this is what we're going to be doing. Yeah, let's do a few more examples, and then we can, if we want to really, we can talk about how we actually get that. It's kind of neat, but it's also totally not necessary if you don't want to see it. So we'll do a few more examples, and then we'll regroup. So let's look at some other functions. Suppose, welcome, the f of xy equal to, oh, can I see your symptom survey when you have a sec? Equal to x squared times e to the 3y. And, thanks, x equal to cosine of t, y equal to sine of t. This is a common parameterization that is often done, right? Like if you're looking at something on a circle, you're just like, oh yeah, I'm gonna let x equal cosine t and y equal sine t. That'd be a circle of radius 1. Or if I wanted to, for some reason, I was on a circle of radius 3, I would let x equal 3 cosine t and y equal 3 sine t. That is something that we frequently do when we're trying to kind of, for whatever reason, say like, we're on the circle and we want to know like what the temperature is over here, over there, and how it's changing. So I want to find df dt. You could do it the long way. The long way would be to actually plug in cosine and sine for x and y. We can do it that way. So f as a function of t is going to be x squared is going to be cosine squared times e to the 3 sine of t. And we could find it by doing the chain rule and the product rule and all the rules. df dt is going to be all right. So derivative of cosine squared is 2 times cosine of t to the first times negative sine of t. And let's label things. Let's call this, I like to be very explicit about my product rule. So there's my f prime, and then we're going to multiply by g. Plus, then we flip it, right? We leave f alone, cosine squared of t, times the derivative of e to the 3 sine t. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff, which will be 3 cosine of t. That's the long way. It's not the way I really want to do it, but it's good to see that it'll work. You can certainly plug in what x and y are and just take the derivative in the usual straightforward, direct, long, painful way. Or we can use the chain rule by making this diagram. So once again, just like last time, our top level function f depends on both x and y, and each of x and y depend on the same variable t. So we can say that df dt is equal to all the paths from f to t. So first the path through x is going to be del f del x times dx dt. And the path through y is going to be del f del y times dy dt. And then we have to find all of them. So del f del x is a little easier, right? The partial derivative of this with respect to x is just, sorry, you can't see that, is just 2x times e to the 3y. And then dx dt is the derivative of cosine, which is negative sine. Plus del f del y is derivative with respect to y, which is going to be x squared times 3 e to the 3y. And then dy dt is the derivative of y, which is going to be cosine of t. Now, these answers aren't going to look the same unless I actually plug in what x and y are equal to. And sometimes, especially, gosh, I've seen some terrible web work problems where people have to like find these super long partial derivatives with all the pieces and then plug in the lower level function. It just looks awful. So hopefully all of you are in Tavernetti's class and not having to do that. But I know the other class, like you have web work homework and it looks pretty gross. If we plug in what x and y are, we're going to get 2 times cosine of t times e to the 3 sine of t times negative sine of t. That definitely looks exactly like that, right? That is certainly the same as that, just written slightly out of order. And here we're going to get cosine squared of t times e to the 3 sine of t times 3 cosine of t. Same stuff. So either way is fine, but usually we view this as seeming a little more manageable. I think it's way easier to take those partial derivatives that way and not have to use the chain rule at the same time. Yeah, I mean, you're kind of shortcutting the chain rule, right? We're using the chain rule, but you're actually kind of avoiding the chain rule in some sense. Right? Because here I had to actually think about, oh, I've got e to the stuff. The derivative is, I have to be more thoughtful there. Whereas here I'm just like, oh, the derivative e to the 3y is e to the 3y times 3. No big deal. I mean, I'm still, okay, fine. I'm still using the chain rule. It just feels a little different. So it can be more challenging. We could look at something like w as a function of x, y, and z equal to x times e to the y over z. I will say, if any of you are in the other 21C class whose professor's name I still don't know how to say, it's T with long last name, there are some terrible like chain rule problems where you have to find like all the partial derivatives. Don't do more work than you have to, meaning some of those partial derivatives, the second piece of them is 0. So if you do the right, so like for example, I saw a problem yesterday where like they were doing this kind of thing and calculating del f del x was super like gross and terrible, and we did it, and then we found dx dt was 0. So we didn't need to do all that work first. So what I'm saying is, if you have to do that web work stuff, keep an eye out for maybe the second part being 0. I know some of them are 0, and don't spend your time doing all this work if you don't have to do it. Okay, so we've got this, and we've also got that x is equal to t squared, y is equal to 1 minus t, z is equal to 1 plus 2t. So now we have w as a function of x, y, and z. And x, y, and z are still all just functions of t. Great, that's not too bad. There are going to be 6 parts to finding the derivative though. So I want to find dw dt. It's going to be del w del x times dx dt plus del w del y times dy dt plus del w del z times dz dt. I think you all should do this. I'll give you 2 minutes. At home too. So here's what you should be getting. So del W, del X is not terrible. It's just e to the y over z. Dx dt is 2t. Del W, del y, okay, partial with respect to y, have to be a little more careful. So you're going to get x as a constant times the derivative of e to the stuff is e to the stuff times the derivative of y over z is just going to be 1 over z because we're differentiating with respect to y. dy dt is -1. Thirdly, del W, del z is probably the worst of the three partials to take. Again, it's going to be x times e to the stuff times the derivative of the stuff. But now the derivative of y over z is negative y over z squared. Or if you prefer, right, y over z is really y times z to the negative first. And the derivative there with respect to z is negative y times z to the negative second. Or negative y over z squared. Times the derivative of z with respect to t, which is 2. And there isn't really a good reason to do anything more with this, unless someone asks you to actually plug in x, y, and z. So you could plug in x equal to t squared, y equal to 1 minus t, and z equal to 1 plus 2t. But I really wouldn't unless someone made me. Right? Like, there's no good reason to do it at this stage. Okay. Let's look at something slightly different. Well, not slightly different, just a little more complicated. So let's say we have the following. Let's say we have z as a function of x and y. It's the inverse tangent of x plus 2y. And we also have that x is equal to r squared times t, and y is equal to r times the natural log of t. So now when we make our diagram, things are going to look a little more complicated. I'm always going from top down. So when I look at this, I'm saying to myself, okay, what variables is z a function of? Just x and y, right? I mean, really just like, what is z equal to? Oh, inverse tangent of x plus 2y, great, it depends on x and y. So at the first level, I'm like, okay, z depends on x, z depends on y. And then I look and say, well, what does x depend on? Oh, x depends on r and t. So I'm gonna write x depending on r and t. And y also depends on r and t. Doesn't matter which order you draw them in, as long as from top to bottom, it's the same sort of way. So z is above x and y are above r and t. And then all the paths. So to find, now listen to my language here, to find del z del r, not dz dr, because z is a function of, at the lowest level, r and t. So I'm finding the partial derivative of z with respect to r. We're just going to find all the paths from z to r. And it looks like there are two. There's one that goes through x, there's one that goes through y. So del z del r is going to equal del z del x times del x del r plus del z del y times del y del r. And they are all del's because they're all partial derivatives because each level is depending on more than one variable. Okay, so then it's just literally taking derivatives. So del z del x, the derivative inverse tangent. Oh, what's the inverse tangent? 1 over 1 plus whatever squared. So this one's going to be 1 over 1 plus your stuff squared times the derivative of your stuff, which in this case is just 1. Right? The derivative of x plus 2y with respect to x is just 1 plus 0. You don't really need to write that, but it's good to point out we know what's going on. And then del x del r is going to be 2rt plus There's my del z del x. There's my del x del r. Del z del y is very similar. Derivative of this with respect to y is 1 over 1 plus my stuff squared. But now when I multiply by the derivative of the stuff, it's going to be multiplying by a 2. Because the derivative of 2y is 2. And the derivative of x is 0 with respect to y. Times the derivative of y with respect to r, which is going to be just the natural log of t. Sorry, good job, James. That part there is your del z del y. That part there is your del y del r. We could simplify this. I don't. Again, right? That's not. You could write this all as one big fraction if you really wanted to, right? Like you could write this as 2RT plus 2 natural log of t all over 1 plus x plus 2y squared. Yeah. Because I was differentiating with respect to what variable? Right. That's a good question though, right? So, right, the reason I got natural log of t here is because I was finding del y del r. And so here I just have r times a constant. And the derivative was 1 times the constant, which is natural log of t. Let's find the other partial derivative of z. Let's find del z del t. So here's the nice thing about this. We've already done half the work. We're still going to have del z del x and del z del y, right? Those are still going to show up. It's going to be del z del x now times del x del r, sorry, del t, apologies, plus del z del y times del y del t. So the first two pieces are still going to be the same as they were before. So I can literally just look at them and copy them. Or if I'm having to like type stuff in, I can copy paste. So I'm going to get 1 over 1 plus x plus 2y squared. I'm not going to write the times 1 this time. And then my del x del t is going to be just r. Oops, you can't see it. Del x del t is just going to be r squared. Plus del z del y, still the same as it was before. 1 over 1 plus your stuff squared times the derivative of your stuff. Times now the derivative of r times natural log of t. The constant is r, it hangs out. And the derivative of natural log of t is 1 over t. So that's how that would work. So most of this is just writing functions as functions of multiple variables and kind of seeing what depends on what. Let's look at a couple more examples. So this next example is similar to a homework question for people who are having to do the web work. It's kind of funky. This is number 11 from section 9.4. That doesn't seem right. Oh, that's because it is from section 9.4 from a different textbook. From a different textbook. How helpful. I've definitely seen homework problems like this. So let's say that z is a function of x and y. And we know that the function f is differentiable. And we know the following things. X is a function of time. Y is also a function of time. We know that g evaluated at 3 is 2. H evaluated at 3 is 7. G prime of 3 is 5. H prime of 3 is -4. And finally, f, the partial with respect to f, the partial of f with respect to x at the point 2, 7 is 6. The partial of f with respect to y at the point 2, 7 is -8. And with all that information, we're going to be asked to find dz dt when t equals 3. So you might look at that and start thinking, what is going on here? Well, a couple observations, first of all. If t equals 3, so if t equals 3, then x is equal to g of 3, and g of 3 is 2. And y is equal to h of 3, and h of 3 is 7. Okay. If I were doing this, which I am, I guess, I would start just throwing the chain rule formula at it because that seems reasonable. I always hate when they do these kind of things in that I want to be like, okay, z depends on x and y depend on t, but I have to kind of remember that z is f. So I'm going to write z equals f. They really are the same thing. We've just decided it's convenient to call them different names sometimes, which is annoying, but it is often done. And then z slash f both depend on x and y. I should say both. Z slash f, which are the same thing, depends on x and y. X is also secretly called g. Y is also secretly called h. Not really a secret. Right? We know that x is g of t. Y is h of t. Is told to us in the problem. And then x and y, also known as g and h, both depend on t. So if I want to find dz dt, I'm just going to use the usual formula first. It's going to be, well, I'm not going to write del z del x because I don't have that written down. I'm going to write del f del x. How fun. And then I'm going to have dx dt plus del f del y times dy dt. Okay, so del f del x, another way of writing that is fx. Dx dt, another way of writing that would be g prime, right? If x is g, dx dt could be written as g prime of t. So here's what we've got. We've got fx evaluated at x comma y times g prime of t plus del f del y is fy at x comma y times dy dt, which is h prime of t. Seems kind of funky, but now we have all the information we actually need, believe it or not. So if I want to find dz dt when t equals 3, well, if t equals 3, we have to remember that means that x equals 2 and y equals 7. We set that up here. I'm going to have fx at 2 comma 7 times g prime of 3 plus fy at 2 comma 7 times h prime of 3. And then we know all those things. That's going to equal 6 times 5 plus -8 times -4, which is some number, 62, I think. It's kind of a weird, contrived example, but it is a question I've seen on homework, so it seemed reasonable to go over. Yeah, we should probably talk about that too. So one other thing you can do with the chain rule, which is kind of neat, is you can use it as a shortcut for implicit differentiation, like back in 21A. Yeah, 21A. So, for example, let's say we wanted to find the derivative of x cubed plus y squared plus x e to the y equal to 7. And I want to find dy dx. The assumption being y is a function of x. So the old school way of doing this would be with implicit, right? We would say, okay, differentiate both sides. I'm going to get 3x squared. Derivative of y squared is 2y times dy dx. Derivative of x e to the y, I have to use the product rule. It's going to be 1 times e to the y plus x times the derivative of e to the y, which is e to the y times the derivative of the stuff, which is dy dx, equal to 0. Right, derivative of 7 is 0. And then we would do the algebra of solving for dy dx. So I would group the dy dx things together on one side. I would bring the other stuff to the other side. So I would say I have on the left dy dx times 2y plus x e to the y equal to, on the right hand side, a negative 3x squared minus e to the y. And then I would divide by this, and I would say that dy dx is equal to, I'm going to factor out the negative 3x squared plus e to the y over 2y plus x e to the y. That is certainly one way of doing it. But there's another way of doing it, which is kind of cool. So here's what we're going to do. We're going to reverse some room here. So we're going to say, well, here's our function again. And we're going to let f as a function of x and y equal this part over here. Actually, we're going to bring the 7 over too. So we're going to say that f of xy equals x cubed plus y squared plus x e to the y minus 7. And that should be equal to 0. Right? If this stuff equals 7, I subtract 7, it's going to equal 0. Okay. So now what we're going to do is we're going to say, well, I'm going to say that my function f is a function of what two variables? Well, x and y. But also, and this is where the diagram, I always feel like this diagram felt tricky to me when I was a student, y also depends on x. Right? We're making we made that assumption over here, right? We were assuming that y is a function of x. If we can do it there, we can certainly do it over here. It's totally allowed. So if I take the derivative of f, well, let's see here. So the derivative of f, I need to find all the ways to get from f to x. So one way of getting from f to x is fx. The other way of getting from f to x is through y. So it's going to be fy times dy dx. So that's the derivative of this side, right? So over here I have, this is the derivative with respect to x of f. Okay, that's this side of the equation. The right side of the equation is 0. What's the derivative of 0? 0. Okay, check this out. It feels kind of like we're cheating a lot, but it's total. So let me back up a little bit. So, right, we took our equation, x cubed plus y squared plus x e to the y equal to 7. We subtracted 7 from both sides. So we had then x cubed plus y squared plus x e to the y minus 7 equal to 0. And we're just calling this left-hand side our function of x and y. That's all we're doing. And then we're saying, all right, we have the equation f equal to 0, where f depends on x and y. Now we are differentiating both sides. So the left side, well, the derivative of f is all the ways to get from f to x. Del f del x, del f del y times dy dx. It's exactly what we have right there. The derivative of the right-hand side is just 0. And now here's the fun part. Solve for dy dx. All right, so subtract fx. So fy times dy dx equals negative fx. And then dy dx equals negative fx over fy. Now let's actually do it. So in this particular problem, dy dx equals negative. So looking at my original function, what's fx? Well, it's the partial derivative with respect to x. So that's going to be derivative of x cubed is 3x squared. Derivative of y squared is 0. Derivative of x e to the y is just e to the y. Divided by fy. So the partial with respect to y is going to be 0 plus 2y plus x e to the y. Oh, look, it's exactly the same thing. Which makes sense because we literally are solving for the same thing, right? We found dy dx here, we got a thing. We found dy dx here, we got the same thing. If your instructor hasn't talked about this formula, I wouldn't sweat it too much. Like it's kind of a neat oddity, but it's not super important. Like if someone gave you this equation and said find dy dx, you could totally do it the old 21A implicit differentiation way, and that would totally be fine. But this is kind of a little bit of a faster way of doing it. Let's do one more example, just to kind of show you one more example. Excuse me. Let's say we had x squared plus y squared plus z squared equal to 3xyz. And I want to find the partial of z with respect to x. So there's two things to do when you're doing a problem like this. The first thing is you need to bring everything to one side. So one, rewrite this as x squared plus y squared plus z squared minus 3xyz is equal to 0. And then think of this as your function of x, y, and z. And then the nice thing is that whatever you're trying to find, del whatever, it's always going to be the negative of the partials in the flipped direction. Meaning if I'm trying to find del z del x, it's going to equal negative fx over fz. And we're going to treat y like a constant. We can also do it the long way, right? Or not the long way, but the writing that way, right? The idea here is I'm thinking of f. If I'm trying to find del z del x, I'm going to treat y like a constant. I'm going to think of f as a function of both z and x. If I'm trying to find del z del x, I'm thinking of z as a function of x as well. So taking my derivative of each side with respect to x. So on the left-hand side, the derivative with respect to x of f is going to equal, well, there's two paths to get to x. There's from f to x. There's from f to x through z. So that's going to be the partial of f with respect to z times the partial of z with respect to x, which is del z of x. And that's going to lead us straight to that. So the really, really short answer is if someone asks you to find a derivative implicitly like this, but using the shortcut, whatever your partial is, del something over del something, it's always going to be negative f, right? That thing ends up there, that thing ends up down there. They switch places. Always works. Kind of neat. Kind of weird. I'm not going to lie. It's kind of weird, but it's neat. So in this problem, fx is 2x plus 0 minus 3yz. Fz is 2z minus 3xy. And that's your answer. If you want to, you can check by doing it the long way. In a similar way, we could find del z del y. Straight away, it's going to be negative. I want you all to do this one. Del z del y should be negative f something over f something. Yeah. Left-hand side. And this is the right-hand side. So del z del y should be negative fy over fz. Right, I'm really just taking the variable on top and putting it in the bottom, the variable on the bottom, putting it on the top. That's the shortcut way I always know what to do. And then fy is going to be 2y minus 3xz. Fz is the same as it was before. It's going to be 2z minus 3xy. Okay, we got time. Yeah. Yeah.
Great. Two good questions.
Okay.
Why are we putting a negative sign in front of like the F?
Sure. So it's coming from this here. So let me ask, are we cool with this? Okay. So if I solve for del z del x, I have fz times del z del x equal to negative fx.
Oh, like the original equation.
Right. And then dividing both sides by fz, I get del z del x equal to negative fx divided by fz.
And then for finding like the actual version for FYC, and it's in the top of the for the bottom part.
So
Why am I
so one more time, sorry.
what are we putting in here? I mean, like, why are we putting like the if we have the 2y minus 3xc underneath it? It's like
2z minus 3xy.
yeah.
So on top, that right there, that is your fy.
Yeah.
Down there, that is your fz. Yeah. So let's talk about the gradient. Gradient and directional derivatives. So let's look at this example. And I can't remember if we talked about this one before or not. So my favorite example for talking about the gradient is the function f of xy equal to 9 minus x squared minus y squared. It's a great function. It looks like a mountain. It's an upside down paraboloid. It looks vaguely like this. It obviously keeps going down and down and down. But if I cut it off at the xy plane, it's going to have this sort of shape. Y-axis. Here's my x-axis. Here's the axis. And it has an intercept of 0, 0, 9. It's got other intercepts too, right? 3, 0, 0, 0, 3, 0, etc. Now I'm going to look at a level curve. I'm going to look at a level curve at the height of 4. And specifically, on this level curve, I'm going to look at the point 1, 2, 4. That point right there is the point 1, 2, 4. We can definitely find partial derivatives of this function in both directions at that point. So they're not hard to find. Fx is the derivative negative 2x. And fx evaluated at this point is going to be negative 2 times 1, which is negative 2. Fy is negative 2y. And fy evaluated at that point is negative 2 times 2, which is negative 4. So what we're saying at that point is that if you traveled purely in the x direction, you'd be traveling in the direction where your slope was negative 2. So specifically when I say traveling in the x direction, I mean traveling in the positive x direction. So if I move in right, if I move from quote unquote left to right on the xy right in 2 dimensions, or in this setup, I'm moving towards you. If I'm sitting at this point on the mountain, right on the front side of the mountain, I move towards you, I'm going down the mountain. And I'm going this way. And my slope is definitely negative. On the other hand, if I travel purely in the positive y direction, this is where my picture probably starts to fall apart a little bit. I think it'll be all right. Sorry, drawing this is always a challenge for me. If I travel purely in the y direction, I'm also going to be going downward like that from left to right, which makes sense because my slopes are both negative. So now, what about the gradient? Well, the gradient of f is a vector. It's a vector where each component is the partial derivative of that variable. So the reason I say it in a very kind of broad way, I didn't say it's fx comma fy, is because you can have a gradient of a function of more than 2 variables. So basically the gradient is always a vector, and you write each component of the vector as the next partial derivative. So if my function was a function of like x, y, and z, the gradient would be a vector where the components were the partial with respect to x, the partial with respect to y, the partial with respect to z, and so on. For this function of 2 variables, our gradient is going to be, and how do I want to write this? There's so many ways to write it. You can write it as a vector like negative 2x comma negative 2y. I don't know, what preferred notation are you guys using in class? Are you using i's and j's? No? Okay. Both? Okay. So you can write it like this, or negative 2x I plus negative 2y j. And specifically, the gradient at this point, 1, 2, 4, is the vector negative 2, negative 4, or minus 2i minus 4j. And here is probably the most important thing I can ever say about the gradient. The gradient always points in the direction that if you walk in that direction on your surface, you would be going up the hill as steeply as possible. So the gradient always points you in the direction of steepest ascent. If you think about a map, I imagine most of you have probably at some point seen some sort of topographical map in your life, right? The maps that have like all the wavy lines on them that like go around, they represent different elevations. Those elevations, the way you go up the mountain the most quickly is by crossing the lines the fastest. And that's the direction the gradient points you in, is the direction that crosses all those level curves the most quickly. It's kind of neat. Here's how I would encourage you to view this. So if I think about this level surface here, so here's my XY plane in 2 dimensions. I'm going to take that level surface where z is equal to 4. I almost drew a good circle. All right, so this is my level curve where z is equal to 4. So my equation is 4 equal to 9 minus x squared minus y squared, which becomes x squared plus y squared equal to 5. So it's a circle of radius root 5. And here's the point I'm talking about. Here's xy equal to 1, 2. So I've gone over 1 and up 2. My gradient vector is the vector negative 2 in the x direction, negative 4 in the y direction, which is literally pointing me straight back at the origin. I didn't draw it to size because I don't really need to. So my gradient is pointing me at the center, which makes sense as far as what I just said, because it's literally saying, I'm going to point you back that way, which is going to be the direction you would travel going steepest up the hill. A couple things I want to make clear. I had like things. Okay, so you guys can't see this very well. So I've got my hill, right? The gradient isn't pointing up the hill. The gradient is pointing in towards the center of the hill, right? The gradient's a vector in 2 dimensions, not a vector in 3 dimensions in this particular example, right? So the gradient points you in, and then if you walk inward, well, the hill's in your way. So you have to go up the hill. So that's what but I want to be super, because like that was something that always used to confuse me. So I was like, oh, the gradient points up. Like, no, the gradient points in. And then if you're traveling on the surface of the hill, you have to go up. So the gradient is the direction in which you most quickly ascend your surface. Okay. The reason we're talking about the gradient mostly is because it's going to help us find what we call a directional derivative, right? So we found the derivative in the x direction, it's -2. We found the derivative in the y direction, it's -4. What if I want to find the derivative in some other direction? So here's what I mean. And it's always the drawing of the pictures here. Let's draw this level curve again. So that's pretty okay. So here's my xy point 1, 2. And instead of, so I know that right in this direction, the derivative is equal to -2. And in this direction, the derivative is equal to -4. Right, because again, right, if you think about like, if we're looking top down on this thing, the hill gets lower as you go that way. Come on. Right, the hill gets lower as you go out that way and lower as you go out that way. Your level curves have lower values out that way. But what if I want to find, the slope of the surface if I travel in the direction of the vector. What have I got here? U equal to 2I plus 3j, or 2, 3 if you prefer. Okay, so approximately, look at my picture here, I'm going over 2 and up 3. So I'm going more up than over. So maybe something like that. I want to know what the slope is in that direction. This is where things get a little wonky. So here's what we're going to do. We're going to parameterize the line that contains the vector that we're trying to go in the direction of. So let's parameterize parameter. You think I would be able to tell that more easily? This is almost my last name. Parameterize the line through the point 1, 2 in the direction of the vector we're interested in, which is the vector 2i, 3j. So we can do that pretty easily. That's going to be 1 plus 2t and 2 plus 3t. Right, again, just taking my points and adding on t times a vector. Right, we parameterized lines before. It's not like terrible. Okay. Sure. Oh, did I? Fine. Sorry, there's one thing I probably should have also done here. I really need to do that. I don't really want to do it. I probably should. We probably should normalize our vector u because things work better that way. So instead of this, we're going to do it slightly differently. So let's take u divided by its magnitude to get 2 over, let's say the magnitude of 2i plus 3j is the square root of 4 plus 9. And then 3 over the square root of 13j. So what I actually should have done is use this vector instead. I'm going to fix it the cheater way. Still the same line. It's written it slightly differently. I divided each thing by square root of 13. But so let me point out, right? If I'm starting at this point, the point 1, 2, I get that point by setting t equal to 0. And then to get any point in the direction of this vector, I just set t equal to some, like if t was equal to the square root of 13, for example, I'd get the point 1 plus 2, which is 3, and 2 plus 3, which is 5. So I would go over 2 and up 3 to the point 3, 5. Okay, this part's not the terrible part. So now I want to find the rate of change of my function f, or remember f, which is 9 minus x squared minus y squared, in the direction of the normalized u, which I'm just going to call this thing here. Okay, well, in other words, I'm asking to find the derivative, right? If I'm trying to find a rate of change, I'm trying to find the derivative. Well, I could do it the long way. I'm not going to, but check it out. Right? We could totally say that x is equal to 1 plus 2t over root 13, and y is equal to 2 plus 3t, 3t over root 13, and plug those in for x and y, and then take the derivative with respect to t. But instead, we're going to do it the chain rule way. We're going to say, hey, look, f depends on x and y. And x and y both depend on t, right? Because really, this is my x of t. This is my y of t. If I'm talking about going in this direction, x of t is 1 plus 2t over 13, y of t is this. So check this out. My derivative of f with respect to t is going to be del f del x times dx dt plus del f del y times dy dt. All right. Well, I'm going to write this in a very interesting way. This is the dot product of the vectors del f del x del f del y dotted with dx dt dy dt. But look, that there, that's your gradient of f. Right? The gradient of f is just the vector of partial derivatives. And that there, dx dt dy dt, well, dx dt is the x component of your vector u, right? Take the derivative of this with respect to t, you're going to get 2 over root 13. Take the derivative of this with respect to t, you're going to get 3 over root 13. This vector here is just your vector u. So the derivative of your function in the direction of u is just the gradient of f dotted with the vector u. I'm sorry, wrong thing here. This is called the directional derivative of f in the direction of u. So in this particular example, just to kind of actually show you the numbers, we're going to get our gradient dotted with our vector our gradient was -2x, -2y, and our vector was, where'd it go there? Sorry, 2/√13, 3/√13. So that would give you the directional derivative at any point, but we wanted to find the directional derivative specifically at the point 1, 2, 4. So we're going to plug in x equal to 1 and y equal to 2. So we get the vector -2, -4 as our gradient, dotted with 2/√13, 3/√13. So we end up with -2 times 2/√13, which is -4/√13, plus -4 times 3, which is -12/√13, for a final result of -16/√13, which is approximately -4.4. So what we're saying with all of this is, specifically here, if you move in that direction away from the center, your slope in that direction is approximately -4.4. Meaning for every 1 unit you move outward, you move 4.4 units downward. Let's take a moment. Questions, observations, anything you guys want to ask. I will try my best to say something meaningful. Correct. Correct. So just to make sure everyone on Zoom heard that, the direction of the gradient is the direction of steepest increase, or where the directional derivative is the greatest, and the direction in the opposite or the negative of the gradient is the direction of steepest decreased. So the length of that direction, would that just be? Yes, so we can definitely, let's talk about that for a second. So a few observations here. So firstly, the directional derivative, once again, just for everyone, is the gradient. The gradient is a vector dotted with the vector u. I should say, excuse me, apologize, where u is the unit vector in the direction that you want. So I suppose if you wanted to be a little more general, if I was finding the directional derivative in the direction of the vector v, where I know that v isn't a unit vector, I would say, okay, well, that's going to be the gradient of f dotted with v divided by the magnitude of v. I made that really ugly. Sorry. Let's write that again so you can all see it better. So you're going to take your gradient, you're going to dot it with v, and you're going to divide by the magnitude of v. Or divide by the magnitude, right? Either way, it doesn't matter which order you do it in, as long as you someone would do it. So I should point out, we know how to calculate the dot product. Is there a question? Okay. So again, assuming u is a unit vector, then another way of calculating the dot product between two vectors is the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. Right? That's the thing we've said about dot products before, right? It's the magnitudes of the vectors times the cosine angle between them. Great. So how can we maximize this value? Well, first of all, the magnitude of u is 1 because it's a unit vector, or can be made into a unit vector if it isn't already. The gradient isn't changing based on which direction you pick, right? The gradient's the gradient regardless of, right? The gradient just depends on what point you're at, but not like if you're going in this direction of u or that direction of u, right? The gradient is always just partial with respect to x, partial with respect to y. That's it. So what angle do I need to pick to make this as big as possible? 0. So we can maximize the value by making the angle between your unit vector and your gradient vector 0. But if the angle between two vectors is 0, that means those vectors point in the same direction. So the way you maximize the value of the directional derivative is by going in the direction of the gradient. So the direction of the vector is the direction that maximizes the value of the directional derivative. Which again, from what I'm saying, should make some amount of sense. Right? I said before that the gradient is the direction of steepest increase. Well, that's just another way of saying the gradient is the direction where the derivative is the largest. And that's what we're saying here. The direction of the gradient is the direction that maximizes the directional derivative. And then the other thing, which is also true, is that the magnitude of the gradient is the largest the directional derivative can be. So what is that maximal value? Well, we've almost got it written down already. If I want to make this as big as possible, we just said we had to let theta equal 0. If theta equals 0, what are you left with? The magnitude of the gradient times cosine of 0, which is 1. So the maximum value is just the magnitude of the gradient. So the gradient is a vector and it points in the direction of steepest increase. And the magnitude of the gradient is how steep that increase is. It is the steepest slope value that you get. And just to go along with that, if you want to go downhill instead of uphill, turn around. So the opposite of the gradient, the negative of the gradient, is the direction of steepest decrease. It's the direction you want to ski if you're trying to go fast, is the negative gradient. And the magnitude of the slope in that direction is going to be the negative of the magnitude of the gradient because you're going downhill instead of going uphill. But you really it's kind of just turn around, right? That's going to be your steepest declining slope instead of increasing slope. Okay. What else to say here? There's so many things to say. I suppose what I'll say lastly, and then we'll talk more about this on Tuesday, is that the gradient is always going to cross level curves perpendicularly. So if you think about this, if you think about our hill, f of xy equal to 9 minus x squared minus y squared. If I actually drew some level curves, so if I set, z equal to 9, I get a level curve of 9 minus x squared minus y squared equal to 9. I get x squared plus y squared equal to 0. Not a very exciting level curve. It's literally just a point. Oh, yes, of course. If I go a little lower, like z equal to 8, I'm going to get x squared plus y squared equal to 1. Right? Because really, what I'm really doing is I'm saying x squared plus y squared equals 9 minus c. Just to shorten up the work. So that's going to be a circle of radius 1. So there's pretty high level, z equals 8. If z is a bit lower, like z equal to 5, we're going to get x squared plus y squared equal to 4. So we're going down the hill. Oh, wow, my circles are looking really, really hot there. Oops, that's a 5, not a 4. Let's go a little bit lower. Let's go z equals 0. We get x squared plus y squared equals to 9. Circle of radius 3. So you go further and further out, away from the center, right? You're going down the hill. Here's your level curve when z equals 8. Here's your level curve when z equals 5. Here's your level curve when z equals 0, and so on and so on and so on. And if you want to go up the hill the fastest, you're going to cross those level curves perpendicularly. The gradient of f is always perpendicular to level curves.